Okay, so this is the definition of something in simple harmonic motion, is that the only thing acting on it, yes?
If we bring a check, do we make it to 12 then?
Yes, you do. Okay. It is an object that is acting under the influence of a force that is proportional to its perturbation, that is proportional to its displacement from its position of equilibrium. So this thing has an equilibrium position, right, like here, okay? And if I distort it, if I pull it down like this, it moves up and down. And the reason, of course, it does that is that here there's a force that's bigger than its weight, right? So it builds up speed, and it reaches that equilibrium point. And right now there's zero force on it, but it doesn't stop moving because it has inertia, correct? Right? So it keeps on moving, and it goes to some upper position where then it goes, gee, now the force is less than the weight, so it goes up and down, and it basically overcorrects. Now this thing will eventually lose energy because it's pushing air out of the way, right? It'll eventually slow itself down. But anyway, there it is, right? Okay? That is simple harmonic motion. It's simple. What does harmonic mean? I guess it's just because it's sinusoidal, I think is what it is, right? And so people were looking at the thing, and sure enough, let the cat out of the bag. Right? Okay. Yeah, it is. It's going to be, we're going to use our sine waves. We need to be in radians today. All of this good stuff, right? Okay. Here are some very helpful formulas. So write these down. These are your friends. Okay. And it's like, uh-oh, what is this thing? Well, this little Greek letter omega, its uppercase looks like an ohm sign, right? But apparently lowercase, it looks like a crazy W like that. Okay. That omega is basically 2 pi over t. So if let's say it goes around, if the thing goes up and down and its period is 1 second, okay, then it's 2 pi radians per second, almost like it's spinning, right? There's almost a sense here that this thing, there's a notion that this thing actually has to do with rotation, okay? Now the things in red are not in your data packet, but are very useful, okay? This t here is period. That's time for it to go from the top back to the top, or whatever, to complete one full cycle, right? That's the period. This thing is called angular velocity. And its units are radians per second, really. And remember, radians aren't really a unit at all, right? They're just like length per length kind of a thing, right? And that's the period. Period is in seconds, okay? And then period and frequency are reciprocal concepts of each other, right? So frequency is 1 over period. So think about this, okay? If I have a period of 1 second, doesn't that mean one cycle is happening every second? That's how frequent it happens? 1 cycle per second, yes? What if I have a period of 1/10 of a second? How many of those fit in 1 second? 10 of them, right? So if this is 1/10, the frequency is that there are 10 of them happening a second, right? So frequency means just that. It's the frequency that they happen. How many per second, right? So this is cycles per second. And a cycle is not really anything. It's just a per second notion, right? It's cycles per second. And cycles per second, you can write that. That's hertz, like the rental company. And you can abbreviate it HZ. But really the units are just seconds to the -1. They're all the same thing. And in German, it's actually spelled not Herz, but Hertz. So Z is always like a T-S sound like that, right? That's crazy. And then this is T. This is our frequency in seconds. And then a simple substitution would show you that, do you see how to get the second one, or the third one up there? That omega is 2 pi f. Do I need to show that? I don't need to show that, do I? Because this is 1 over t, isn't it? Right? So the omega is also equal to 2 pi f. Not in our data packet, so I'll put these guys in blue. And then we've got our little equations here. And there's two equations for position, two equations for velocity, right? And you guys, when you get into calculus and start taking derivatives, anybody know how to take the derivative of sine? Not yet. Okay. So that won't make sense to you yet. So the position is its amplitude times the sine of omega t. Yeah? The velocity then is the maximum velocity times the cosine of omega t, right? Now what does sine look like? Starts at zero, at time zero, right, and goes upward, doesn't it? In a quarter of a cycle it's at the top, half of a cycle it's back to the middle. In 3/4 of a cycle it's down at a maximum, and at a full cycle it's back to zero, doesn't it? That's what a sine wave looks like, right? Okay. Okay. Yeah. Right. That's what sine wave. That's a full cycle of a sine wave. That's what it looks like, right? And a cosine. What does a cosine look like? Well, cosine's a little harder to draw, right? It starts at a maximum, doesn't it? Yeah. Okay. And then in a quarter cycle, it's at zero, right? So it's like that, right? At this point here, it's at a negative maximum, isn't it? Yeah. Now, I'm very bad at drawing this, right? Okay. At here, it's at zero, isn't it? Yeah. And then at here, it's a negative maximum, isn't it? It's like a crazy thing like that, isn't that? That's a terrible cosine, but there it is. Yeah. Cosine does something like that, doesn't it? Okay. So let's just take a look at what it really does. Let's go to this, right? Okay. And let's get it going up and down. This thing will map where it is, right? So there it is. That might be a little too robust for us, but maybe not. Okay. I think I'm clicking. I think I'm moving my mouse. Piss switch. Okay, there it goes. Okay. Now, why does it look distinctly like negative sine? And this is something that always threw me off as a student, right? It's like, well, that's the same as it, because it's just where I started. It's arbitrary, yes? Right? So do you see that this is just an arbitrary equation for the position? That it could be negative sine, it could be negative cosine. It could also be, by the way, some sort of a shift, couldn't it be? Right? Like doesn't even start at any of those, right? We start looking at it at some random time. But let's make this look like the drawings that we have. Gosh. Can you read it here? There you go. You're like freaking inches from it. Okay. So let's go in here. This looks to be about the middle, doesn't it? So if we want to start it as a sine, we make it 0.71, right? Now it looks like a sine, doesn't it? Hey, there we go. Now we've got the right relationship, don't we? Isn't that beautiful? Right? This thing up there is a sine wave, right? This thing down here is a cosine. That's the velocity. Now I'm going to risk teaching you something, okay, that you don't already know. And that is that velocity is the rate at which position changes, correct? Rate at which it changes is the slope. Isn't that right? The rate at which a function changes is its slope. You'll learn that this is called the derivative of something. Now, take a look at these two things, right? Here you have a maximum upward slope, maximum positive number. Isn't this a maximum positive at the same time? Yes? Isn't the slope right up at the top? What is that slope? A tangent line would be? Zero, level, yes? Right? Is this thing cross zero at the same time? Brody, I need your eyes up here. Yeah, doesn't it cross zero at the same time? Yeah, that's beautiful, right? Here it's a negative maximum right at this point, isn't it? Isn't this also a negative maximum? Yeah, that's beautiful, right? Here we are at zero again. Isn't this zero? Look at that. It's crazy. It's a bit like this, isn't it? Right? But that's the notion here. And we could also talk about acceleration, but I don't have time to do that today. Yeah. Say it again. Oh, okay. Zero is really in here. Okay, don't read the graph. But pretend there's a line reading zero right there. You like that? Is that okay? Yeah. Okay. Pretend it's like really a sine wave. The reason that it's not passing zero is that, of course, it's just reading the distance to there, right? Okay. But there is an equilibrium position that we would call zero. Okay. So let's go back to here. Okay. And I think we've got our formulas. There's another formula that goes along with, and they offer, and they had a mistake in their first data packet where they got this wrong, which I think is funny.